Wait a second, I'll share the document once. Yes, ma. Here we are going to see the second part of sortings today. That is radic sort, heap sort, and some more are there. So we'll discuss them in detail and we'll look at the implementation of it for today. Okay. I'm sharing the screen now. Yes. Are you able to see it?
Yes, ma'am.
Let me increase the font size. Yes. I think now it would be a bit visible. All right. And these are the some of the additional methods related to your sorting, right? So we'll discuss them one after the other. First, we'll go with the concept of heap sort. Heap sort means it comes with the heap tree property. Heap tree satisfies the concept of binary tree, not the binary search tree. Binary tree, what is the property? It should have at most 2 children, not at most, no? At least 2 children it should have. No, I'm sorry. It should have at most 2 children. That means 0, 1 or 2. Right? That binary tree property it should satisfy, and it should keep on filling the leaves from left to right, not from right to left. That means the left shade should be filled first, then go to the right shade. One more conditional addition to it will be added. What is that means? Heap property. What is the heap property? This heap property is of 2 things. One is if the root is having the maximum value when compared with its children, then such kind of tree is known as max heap. Suppose if the root is minimum when compared with its children, then it will be like min heap. Mostly we will be implementing the max heap property. We don't concentrate upon the min heap, but still the min heap property is also satisfied. If you write the max heap property code, if you change the greater than symbol to less than, it comes into min heap only. Right? By small change in the relational operator, it will turn into min heap tree. Right? Depending upon that, how the code will be done and how the complexity will be there and how the tracing of the code will be done, we'll see in this now. Okay? First, initially, we'll have a number of elements in an array. Right? And we are going to satisfy the property of heap. What is that? Max heap. By repeating the process and correcting the positions of it, we are going to perform it. So how much time complexity is required means we are repeating the things only log n times, not n times. So the time complexity will be log n followed with number of elements. So that the overall time complexity will be n log n. Let us see one small example, right? Are you able to see the things or it was blur? I think now it would be a bit visible to you. Right? Think the elements are like this: 4, 3, 7, 1, 9, 8, and 5. These are the elements randomly chosen. So initially the root node is 4, 3, 7, 1, 8, and 5. Now the max property should come into the picture. How it will come? What is that property? And how we are going to do that means, which is the maximum element that we need to make it as a root. That is what max heap conversion. Once you get the max heap on the top, we'll take that to the last location and we'll reheapify the rest of the tree. Once you pick the maximum element, that means the largest element among the list, and we are making it as a root, then after we are going to repeat the process for all the elements. Next max, we will make it as a root. Next max, like that. All the elements, maximum elements, they are made as the root. From the root node, we are moving it to the last node. So that is what achieving the property of heap sort. So here 8, 4, 7, 1, 3, 5 are the elements in the tree. So your maximum element got the root node now. So this is a sorted element. Maximum element is sorted. So please push that back again. So repeat the process again. Ignore that 8. Repeat the process for the rest of the elements. Which is the maximum? 7. So 7 will become the root. Again reheapify the tree. Again construct the max heap. Like that ignore 5. Like that ignore 4. Like that ignore 3. Ignore 1. So the process is 1, 3, 4, 5, 7, 8. Did you got the elements in the sorted order now? So before going into it, we need to know how to construct a max heap. Let me show you one example in the Word document. I'll share the Word document, ma. Are you able to see this Word document? So randomly I'm taking some elements. Previously, whatever elements I have taken, I'll take the same elements. Let me go with that example. Wait a second, ma. Give me 1 minute time. Yes, I am taking the elements as Havi has taken the array elements. 4, 3, 7, 1, 4, 3, 7, 1, and then 8 and 5. These are the elements randomly chosen to perform the heap sort. Okay. Now, how to construct the heap tree? That I am going to teach you now. How to construct the max heap. What is the first element? 4. Right? So 4 will become the root. Is it having any child to verify the heap property? No. So no need to discuss that. What is the next element? 3. So 3 will become the left child of the 4. As the binary tree property, it should have at most 2 children. So 0th children it has there previously. This is the first child now. Right? So 4 left child is 3. I need to satisfy the max property. What is the max property? Always the root should contain maximum value when compared with its children. So which will become the root? Is it satisfying the property? Yes, 4 is maximum element when compared with 3. So root is having maximum value satisfied. Next element is 7. So 7 will become the 4 right child. Yes or no? Yes. Now I need to check the heap property. Left child is satisfied. After inserting the right child, I should check the heap property. What is the property? Root should have maximum. Is it having maximum? No. So please swap 4 and 7. So finally, how your tree will be now? 7 will be the root. The left child will be 3 as it is. Whereas the right child got swapped with 4, not with the 7. So what is the root now? 7, 3 and 4. Is it satisfying your property, heap property? Yes, max heap property, it is satisfying. Whatever the root value is there among its children, it is greater. Now let us go insertion with the next element. What is the next element? 1, which will become the left child of the 3. Now please verify the heap property. Root of 1. What is that? 3. It is maximum. So satisfied with the property. Next, what is the element to be inserted? 8. If I insert it as a right child of 3, please check the property. 3 and 8. Is it satisfying the property? No. So there will be a swap among them. So 3 will be inserted into the 8 position and 8 will be moved to the 3 position. But still it is not satisfied. It is not satisfying the heap property because my overall root should have the maximum value. Now please verify it with appropriate root. 7 and 8. 8 is the greater one. So 7 will be occupying the 8 position and 8 will be occupying the 7 position. Sorry. 8 over here and 7 will be here. Now please insert the next one, that is 5. Will be the left child of it, but the property is wrong. So 4 will be occupying the 5 and 5 will be swapped with the 4. Now please verify it with the root. They are greater, so no need to satisfy. What is your max heap tree now? 8 is the root, 7, 5 are the subchalls. For 7, 1 and 3 are the childs. For 5, 4 is the child. This is what the max heap tree for this particular element. After constructing the max heap, please take down the first root from it, 8, which is the maximum element. So please copy it into the auxiliary array and discard the array size by moving the least element into it. So what is the last node? 4 will become the root now and reheapify the tree. Okay, 4 will become the root, then reheapify the tree. Topmost element got assigned to the top row, so last we are assigning. Like this, if you repeat the process, no, all the elements will be in the sorted order. If I repeat the elements for all it would be easy, right? Now please look at the example. Again, I am showing it. So once in the first step, we have constructed initially the elements with the max heap property. Then after we are continuing with the process of taking the topmost element out here, taking the topmost element aside and reheapifying the tree again. Reheapifying the tree again. Repeating the process until we encounter the single element in the tree. This is how finally you have constructed your array. And please look at the heap program. What is that heap program? What is it? First of all, please take the heap class, builder heap. I have to construct heap tree, no? Heapify property. For that, first constructing the heap sort, one program is there. Then heapify logic is what? Always multiply with 2 plus 1 will give you the left child. Into 2 plus 1 will be giving me the right child. So if it is less, then only I will be shifting it to the max. If not, I will be shifting it to the right. Right? This is what the heapifying logic. Once you heapify it, we are going to swap it. What is that exchange means? Swapping the two positions. A of I will be moved to the A of j. Right? Like that we are performing the heap sort. And remember, we are doing with the Java software. So we need to save the file with Java extension. Then you compile it. Please enter the values. After heap sort, these are the values. Okay? This is what the heap sort. Remember the logic very carefully. Okay? Next topic is decision trees. Decision trees mean these are the trees used to prove that lower boundaries are made for the decisions. Like we are using binary tree to check whether the element is less or greater. We have applied one condition that left less than, root less than, right. If we repeat this particular process, this comes under the decision. Either of the way we have to go to find the result, not to go all the possible ways. Okay, right. So decision tree means we are going to check the conditions. Based upon the conditions, which particular path you want to go to achieve a result, that is very, very important. Suppose to find greatest among 3 numbers, we have the condition that A greater than B and A greater than C. Then only we will move to the path that A is greatest. Like that, I can go with the possible things and achieve the path. This is one example for it. Selection problem means obtaining the minimum element to be opted and all. Okay. Bucket sort, remember this. This is very, very important. Bucket sort is known as a bin sorting. That means it is a specific sorting algorithm. The word distributing the elements we want to sort into several individual sorted buckets. By doing this, we can reduce the number of comparisons between the elements and then cut the sorting time. So what is the steps we need to perform in the bucket sort means? Set up an array, our initially empty bucket. Distribute the elements into their appropriate buckets. Sort each bucket. Concentrate or reconstruct them into the full list back again. So what you are going to do, initially empty buckets are there. Distribute the elements into that buckets individually. Perform sorting on each bucket. Then recombine the full list again back. Okay. Here it was like, first we need to take the elements and divide them and then achieve the things. So here the time complexity is performing upon the bucket sort. In the worst case, it is big of n square. And in the average and in the best case, it will be big of n only. So this is a very simple algorithm where it takes some memory to be performed for the bucket sort, but still it achieves the implementation very simply. Okay, the complexity is reduced when compared with the any other thing. So let us look at the logic of it. First, how many number of elements are there? Please read them. Then please sort them into the, please store back them into the specific buckets and arrange the bucket in an order. Then recombine the bucket. Okay. Here are some of the examples. So here in the logic, first we are taking a bucket. First we are reading the array elements and the n number of elements. Then we are moving that into the specific location of the bucket. We are moving the array list. Then after that, please individually we are sorting them. Individually we are sorting them. How we are sorting? By using the collections dot sort. Right? By that method we are going to sort them. So individually each and every element in the bucket got sorted. From the main function we are sending the arguments like array elements which you want to read it and then the size of the array. And after returning it, we are going to print the result back in the sorted order. This is what the method of your bucket sort. What is there in the bucket sort? Please read the array elements. Then please read an empty bucket first. Into the empty bucket, please arrange the elements. Please concentrate upon the each and every bucket and perform the sorting. Okay. This is what about your bucket sort. Next logic is radix sort. The difference between the heap sort and bucket sort is heap sort will not take any additional memory to store back the elements in any way. By using one single array only we can perform it. Whereas in the bucket sort we need again a bucket and empty bucket. Extra memory is required to sort them and then concrete them again back into the single list. So it was taking memory, but the time will be reduced. Whereas in the heap sort, time will be more, but the memory will not be wasted much when compared with the bucket sort. Okay, this is one of the methods to implement the sorting, that is radix sorting. Radix sorting will be same way like we are performing according to the alphabetical order, right? And there are 26 alphabets in the English. In the first part, the names are grouped according to the ascending order of your first alphabet. If the first alphabet comes for two people, same alphabets means we are going to concentrate upon the second alphabet. Like that, the process will be continued depending upon your alphabetical order. So, even in the radix sort, Depending upon the number of passes, we are going to find the maximum letter for it, and we are going to perform the radix sort for the digits, comparing among the digits in the LSB to MSB. That means least significant bit to most significant bit. We are going to compare the digits among them, which is having the more order that will be placed first. So according to the alphabetical order, we are going to pass it. So think the given example is of some 6 numbers by using the radix sort, sorting the list according to the digits at zeroth place, zeroth place. So zeroth place among them, which is the thing we are having? Zero place lo unna least number enti? 0. So that I am passing it. Next 1, next 2, next 3, 4. Here please concentrate upon the zeroth place. That means the units place. Units, ones, tens, hundreds, like that we are having the number places. Like in the radix sort, we are going to check the first zeroth place, that is the unit place. In the unit place, we are going to check the order now. So first, look at here. Under units place, what are the numbers we are having? 0, 2, 1, 3, 4. Among them, which is small? So 0. That's the reason 10 is kept in the first position. Next, 901. 1 is having no. So 901. Next, 2, 803, 1024. Because 4 is having it the highest priority. Next, coming back to the sorting of your 10th place now. First 10th place, we need to concentrate. Among 10th place, which is having 0, 2. So 0, nothing was there means I can put 0, no? So 0, 2 is the first element. Among them in the 10th place, 1 was there. 10th place, 2 was there. 0 was there. Like that we had so many things. So among 10th place, we are having still 0 also. So 901, 10, 803, then 102. This is what the things we need to perform. Then sorting the list according to the 100th place now. So first zeros, then 8, 9. Among them, now please concentrate upon the 1000th place. Among 1000th place, 2, 10, 8, 9. They are having 0. So they are kept first. So 1024 is the last. So did you understand the sorting by using the numbers place? That means the digits place, units, tens, hundreds, thousands. Among these places, it got represented over there. So please look at the algorithm for the radix sort. This radix sort is very, very important and an easy one. Try to learn the logic of it. Okay. First, initially, we need to concentrate upon each and every number's units place. From then onwards, please increase the digits part. From that, you can change it up till to the 1000 or 100. Okay. The running time of always, it depends upon the n log base 2. That means n log n. In turn, it can be called as preferably called as a quick sort, but it doesn't scan the property of quick sort. Pivot element and comparison will not be there, but still we'll call it as we'll be calling it as which kind of sorting? Radix sort, depending upon the places we are going to perform. So let me list out all the sorting techniques first. First, sorting means arranging them in an order. Among them, first sorting is insertion sort. Making some place and adding the element into the appropriate place is known as your insertion sort. Its time complexity is big of n square. Once you finish the insertion sort, we came to the merge sort. Merge sort follows divide and conquer strategy, where the list will be divided into 2 halves and performing the further division not possible, then start merging and comparing and unique solution will be made. One special thing about the merge sort is, even for the worst and average cases, the time complexity will be big of n log n. There is no issue in it, right? So the next coming up sort is quick sort, which is very, very simple and easy to learn. Quick sort, divide and conquer. One pivot element will be there. Based upon the pivot element, the set of elements will be sorted. Less than will be on the left side, greater than will be on the right side. Process will be continued until you find the single element over there. The next sorting technique today we have learned about heap sort, bucket sort and radix sort. Heap sort follows with the properties of Max Heap. Bucket sort will be followed with the property steps like making empty bucket, assigning them with each bucket, then sorting the bucket and rearranging them into the overall list. Then the thing is like radix sort. Let us take one more example and I'll perform the radix sort again. So please look at this example. I'll just take one Word document. I'll take some more elements. I'll take like this 45. I'll increase the size first. 45, 67, 89, 55, 34, 106, 405, then 1024, then 67, then you are 4. These are the elements. I just want to do the sorting, right? Let me give some spaces among them so you can distribute them. Yes. Okay. How many elements I have taken? 9 elements. What is the first element? 45, 67, 89, 5, 34, 495, 1024, 67 and 4. So first by using the name radix sort. That means we are sorting the elements by using the place value. Sort by using the place value. So first take the place values of units, that is 0th place. What is it? In 0th place, what are the values you are having? 5, 7, 9, 5, 4, 5, 4, 7, 4. So among them, are we having any zeros? No. Are we having 3? No. We are having 4. So I'll be writing 4. Then after, first I'll write 34. 34. Among the list, 34 is the small. Then after 1024. Then after 4. In the list, it should come like this only, no? Then what is the next element? 5. So among the list, I'm having 45 first. 45 followed with 5. Followed with 495. Followed with, now the next number is 67. So 67. 67, I think I have typed twice. I'm sorry, I'm deleting it. Yes. Next, after 7, we are having 9. So what is the element last we are having in the radix sort? 89. Did we get all the elements? 3, 6, 7, 8. 3, 6, 7, 8. So we got all the elements what we have in the main list. By using the first part, that is the 0th element sorting, we have done with the list. That means 34 is the smallest. 10244, 45, 5, 495, 67 and 0. Please sort it by the value of tens now. By the tens place, I just want to sort it now. What are the values in the tens place? 3 we are having under 34. 2. For 4 it is 0. For 45 it is 4. For 5 also it is 0. So which comes first? 0, 4 and 0, 5. So 0, 4, comma 0, 5. Yes. The next element is after 0 we are having, are we having any value with 2? Yes, 1024. So 1024. After that we are having 3 value, that is 34. After that, in tens place, we are having 45. After that, we are having tens place, 67, then 89, then 495. By using the tens place, the list is like this. Now, we'll be concentrating upon the hundreds place. So first, are we having any hundreds value? 0. Obviously, they are there. So hundreds also 0. Okay. Here 0. Here 0. 0. 0. Here 4. So all this will be as it is. Nothing will be there. So the list will be as it is. Because everything was there properly. 4, 5, I'm sorry. 1, 0, 2, 4. Because under a hundreds place it was having 0. And that was in the list. So obviously it remains like that only. Then 45. Then 67. 89. 495. Because in hundreds place 4 was there. Right. This was a list after the hundreds place. Now we will concentrate upon the thousands place. Yes, after this thousands place, anyhow 4 will be there as it is. 5 will be there. Please look at here, under thousands we are having zeros first. So we need to write 34. We need to write 45. We need to write 67. 89. Then in the thousands place of 495 is also 0. So write down that. Then the thousands place 1024. Please look at this. Is the list is sorted or not? Is the list is sorted? Yes, is the list is sorted?
Yes, ma'am.
Yes, this is what we'll do in the radix sort. Okay. Sorting of the elements is done by using the radix sort. And here is some logic for it. Before going to the searching techniques, are you comfortable with this radix sort?
Yes, ma'am.
Okay. I'll move to the next part of searching. Searching means what? Yes. Yes. First, we are going to find the element which we want to find it in the list. So searching means finding whether the given element is present in the list or not. We are having different searching techniques. Linear search can also be called as sequential search, jump search, binary search, interpolation search, Fibonacci search, exponential search. Among them, we are going to learn 2 different searching techniques for today. Okay. First, look at the linear search, that is the sequential search. What we do in the sequential search, we'll start comparing the first element with the given element. If the matches continue, element is formed. If not, we'll repeat the process until we encounter the end of the list. So what is it, ma? Linear search means first take some array and read the element which you want to find it in the list. Then repeat the process that the element which you want to search, that is the item, is compared with the array element. If they are equal, element is formed. If they are not equal, please go to the next element and repeat the process until you encounter the end of the list. Suppose you take the array elements like this. Array elements are 77, 56, 14, 7, 18, 66, 21, 43, 23, and 10. That means 10 elements are there. And now we need to find some element is present in the list or not. What is that some element? What is that element you want to search it? Element value. Tell me one example. I want to search 18 is there in the list or not. So my searching element is 18. So what I will be doing in the first iteration? First I will compare it with the 77. And remember the point that for the linear search, there is no condition that it should be in the sorted order. The list should be in the sorted order. Like that, pre-request site is not required for the linear search. The list can be in any order. So first, the element X will be compared with the searching element, right? A of I will be compared with your item. Item I just want to search is 18. 77 will be compared with 18. Is it equal? No. So I'll increment the array. That is, I'm moving to the next element. That is 56. Is 56 equal to 18? No. Then what I'll be doing? I'll be just changing my array index. 14 will be compared with 18. Are they equal? No. Please increment the array index. 7 will be compared with the 18. Are they equal? No. Then 18 will be compared with the 18. Both are equal. So in this present scenario, it is there in the location. Which location? The fourth location, the element is present in the list. Right? This is what linear search. Comparing the given element in the list by one after the other. This is what the linear search. Suppose if the element is not present means it will be returning nothing for you. Right? The space complexity means how much space requirement, how many number of elements are there in the list, that much space will be required. The time complexity in the best case, suppose the searching element is the first element, the best case will be big of 1. The average case and the worst case will be big of n. So because it has to repeat the process for the n number of elements. Only the best case, that means in the first occurrence only, the searching element is acquired means it will be big of 1. Rest all the things it will be big of n. I can't make sure that it repeats only for 2 times or 3 times or 4 times. It may repeat to as many times as it can. So this is what the list I just want to. And even the duplicate elements are also available. If there is a duplicate element in the list means it will return the first occurrence of the element whatever you are searching for. Okay. So please look at the logic for the linear search. Please look at the logic. In the void main, we are reading the array elements and we are sending that which element we just want to find. Right? Now, if the answer is obtained Boolean true, element is formed. If not, element is false. So please start comparing with the values. If I equal to B, then return true. If not, return false. Okay, if the element is not present, what you are going to do? You are going to tell that element is not present in the list. Okay. Are you comfortable with this? Linear search?
Yes, ma'am.
Okay. Before going to the next search, I just want to revise the linear search once. Linear search means it will take an input array and the element which I want to search in the list. Even one request site is there in this linear search. The list pre-request site was not there. The list can be of any type, whether it is sorted or unsorted or duplicate elements, whatever it is, it can have anything. But the process is like whatever the element you want to search in the list, it will be compared with the element in the each and every element in the list. Right? First element it will be compared. If it matches, it returns true. If not, it will go to the next element. Until it reaches the end of the list, it will keep on comparing with each and every element. So what could be the disadvantage means, suppose I have 100 elements and I just want to search the element 99th element I want to search. So 98 comparisons were false. Under the 98, 99 search, I'm finding that the element is present. So this is what very time consuming searching technique. So the better one than this is binary search and the jump search, which we are going to learn now. So please give me 1 minute time. Yes, coming back to this jump search, this is a like you are, I can tell it like when you are listening to a song in your tape recorder on your cassette, there are 6 songs obviously. All may not like all those 6 songs. You just want to go forward. That means you just want to go skip one song and jump to the next one. That is what the technique we have implemented over here. So a better time complexity will be there when compared with the linear search. Okay. Try to learn this jump search clearly. Iteratively, we are going to forward or backward depending upon our search, and it depends on the gap between each and every element what you want to search it. Okay, right. And there is a disturbance with my network, so actually there is a power cut in my home. I'm sorry if I'm not available with this. I'll continue it in the next class. Okay.
Okay, ma'am.